I caught a mouse. All right, we are checking out the next part, which is rational functions and asymptotes. It's one of my favorite words in math. That guy's an asymptote. I slipped on the ice and fell on my asymptote. Let's try a little warm-up just to keep it fresh. So we're just factoring, so it's got to be a y and a y equal to 0.
5 and 2, negative 5 and negative 2, which should be fine, and so x has to be 5 and x has to be 2. That's fine.
All of this, like this is 1y squared, and all of this is another y, and this mirrors this equation exactly, right? We've got one of these things squared, one of these y's squared. I have -7 of those things, -7 of those things, and plus 10. So we can say, hey, I know that all of this junk is the y, and I know that it either has to be equal to 5 or it has to be equal to 2. So you could say, oh, so x squared plus 1 should be equal to 5, or x squared plus 1 has to be equal to 2. You solve, you get x squared is 4.
So x is plus or minus 2. Or x squared is equal to subtract 1 and take the square root, so plus or minus 1. Sweet, so 4 different solutions possible.
We're looking at rational functions and asymptotes. Rational functions, the word ratio means like divide, so 1 over x is the parent function. Y equals 1 over x. If you type that in your calculator, you'll get something that looks like this, right? And it goes that way forever, and it goes down forever, and it goes up forever, and it goes over that way forever. So there's a lot of skewing. They have a couple interesting pieces that we'll talk about in a second, but mostly this is a weird function because it's discontinuous. We're used to nice functions that are continuous, like quadratics. It's a parabola. Or linear, right? Discontinuous functions, even weird functions like that you can't quite make an equation out of, that don't have any breaks, are continuous. But this is a discontinuous graph because it goes down, 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 gets really close to the y-axis, and then but doesn't actually hit it. And in fact, it sort of like teleports to this other side and then comes down, down, down like that, right? It's a little weird. And if you move my head out of the way, Gorkiewicz, that guy's an asymptote. This is another hyperbola. Right? It goes up, 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 and it stops somewhere up there and pops back into existence down here, turns around, and comes back down like that. Weird, right? Those are discontinuous. They have gaps or breaks. Continuous has no gaps or breaks. It's continuous. Continuous. All right. So this is a rational function. I'm still here. Let's park myself over here, huh? This is a rational function, and like a rational function is y over y equals 1x. That's the parent function. That's a little bit hard to see what's going on, so I think of like cookies. Yeah. Let me squeeze this down a little bit. It's a ratio of two polynomials, or just a ratio of two things. We're just dividing. It's division. So if you think about cookies and dividing cookies up, this is like the number of cookies. Oh, I was hiding back there. This is the number of cookies based on the number of people n that we're sharing with, right? So how much cookie everybody gets. Cookie per nerd, maybe. So if you have one cookie and you're dividing by some people, you're taking a cookie and breaking it up. So if we go C of 1, it means you're dividing one cookie by one person, and so that person gets the full cookie right there. Bam, here. That's mine. Yeah? If you're talking, so on the graph, you'd have 1, comma 1. Yeah? C of 1 is 1. If you took a cookie, if you took C of 2, you took one cookie and divided by two people, everybody gets half a cookie, right? You take one cookie and you break it in half. This person gets that cookie, that person gets that cookie, and so you go 1 and then a half. So, two people and a half. So this is 2, 1, 2, yeah, 1, 2 right there, right? And if you played the same game with this, if you said, I'm choosing 4, just for fun. If you said C of 4, you're taking one cookie and dividing by 4 people. That means everybody gets a fourth of a cookie, right? And you can see this happening at 4. This is about half of the half. If you keep doing this, if you take one cookie, if you're looking at C of 10, you get a tenth, no problem. That's not a big deal. There's 10, that's a tenth. A 15th, a cookie, if you're dividing among 15 people. But think about this. If you divide, if you take a cookie and divide by 100 people, everybody gets like a little crumb, right? 100th of a cookie. That's pretty small. If you divide by 1,000, everybody gets like 1,000th of, like, that's the smell of the cookie. If you divide by 1,000,000, right? Everybody gets just like, I don't know, can see it, like a little tiny piece. But nobody ever gets negative cookie. Does that make sense? Like, even if you divide one cookie by a ton of people, 1,000,000,000 people, you never get a negative answer, right? Never get negative cookie. Probably people are negative because they wish they had more cookie, but the cookie themselves itself isn't negative. So this will approach 0, but basically all of them get no cookie. This will approach 0, get really small, but it won't turn negative, right? That behavior we say is asymptotic. I like that too. That guy's behavior is asymptotic. It means it approaches this limit of x, but it never crosses it. Likewise, this approaches the y-axis asymptotically. You could think about it this way. If you gave a cookie to me, it's only this big. That's fine. But if you gave a cookie to my daughter, she's smaller than me, so the cookie appears much bigger to her. So effectively, it's sort of like me eating 2 cookies. If you gave it to an ant, you could feed a ton of ants on one cookie. It's sort of like the cookie gets bigger and bigger and bigger depending on if your person is smaller and smaller and smaller. I don't know, it makes sense in my head. You could also look at it this way, is that if you were dividing by, if you're taking like C of a tenth instead of C of 1, if we say C of a tenth, that's really saying one cookie divided by a tenth of a person, small person, I don't know. And this is, if you multiply the fraction, you get 10 out of it. And so if you did C of 1/1000th, which is really close to 0, you'd get 1 over that fraction, which is just the denominator, which is just 1,000. So it gets big, 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 but never crosses over negative. It never crosses this way. Right? Okay, so that's just kind of a rundown of those. If you graphed this 1 over x, this is what we've only been looking at this side. One cookie divided by 1,000,000,000 people is close to 0, but it's not negative. One cookie divided by really tiny people is really a big amount of cookie. You can play the same game with negative numbers. If you divide one cookie by negative 1,000,000,000 people, you get really close to 0, but approaching it from the bottom, right? This is a tiny, tiny number, but it's a tiny, tiny negative number, right? And if you do the same thing, if you do 1 divided by 1 over negative 1,000,000,000, this is gets really large in the negative sense, right? It goes up in a negative value. So this shape is called a hyperbola, and that's kind of what we're going to look at. The domain of this is any x values, right? I can put any x values in. The only thing is I don't get an x value of 0. It never hits 0 because I can't put 0 into this. I can't divide by 0. Previous video talked about that a little bit. So the domain is all of it, but not 0. And the range is all of it, except I never get 0 also. So for the parent function, that's true. Talk about like the pieces we need to graph this. One of those pieces is the zeros. It's like where the graph hits the x-axis, if possible where it hits the y-axis. This is called the vertical asymptote, where it has this big freak out. Yeah, that's the vertical asymptote. And the horizontal asymptote is this flat part that it approaches as we get really big or really small numbers. So those are the 3 things we're going to try to look at and find out how to do that from an equation. Okay, so the first thing we're interested in finding, ooh, I disappeared. I can't see, I'm blind, I'm blind. Oh, there I am. I could actually see, don't worry. That guy's an asymptote. One of the first things that we're interested in finding is where these things hit the axis and maybe the y-axis. So from these you can simplify if possible. This I can't simplify. And then if I want this to be 0, really easy to see where it hits the y-axis. I know at this point the x is 0 and the y is something. So you can put zeros in for the x's, and you get y is 2/3. 0 plus 2, 0 plus 3, so 2/3. So that's where it hits the y-axis. The x-axis is a little more challenging, but not really. It hits somewhere on the x, but 0 for y. And we can substitute in for the y value. We set this equal to 0. We say this is 0. So you get x plus 2 over x plus 3. I want to know when that equals 0. Multiply both sides by the denominator. 0 doesn't care. This cancels out effectively, and you're left with 0 equals x plus 2. And so you can solve and see it hits at x is -2. Now, there's a shortcut, which is just set the numerator equal to 0, because this trick with the denominator canceling out happens all the time. So that's easy to find those two spots, right? That's how to find the zeros. That's great, but I want to know what's happening when this big freak out. I want to see where this big vertical freak out happens. That's called an asymptote. The vertical asymptote, we sometimes abbreviate it VA. We want to know what's going on there. Looks like it's happening at -1, 2, 3. And it's the part where at -3, like I can put in 5, right? If you put in 5, you get 5 plus 2 is 7, and you put 5 in there, you get 8, and 7/8 is fine. And I can put in 0, right? If I put in 0, I'd get 2/3. That's what happens here. But if we put in 3, you'd get 5 in the numerator. Oh, sorry, -3. You get -1 in the numerator if we put in -3 into here and here, -3. But you get 0 in the denominator, and that can't happen. We can't divide by 0, and so as we were looking at before, you get this big vertical aggressive increase. That's vertical asymptotic behavior, right? It's because you're effectively
dividing by 0.
That's easy way to find the vertical asymptote is simplify if you can, and then set the denominator equal to 0 and solve. So this is pretty ugly, but we could factor it a little bit. Numerator factors into this, denominator factors into that. The top and bottom cancel out. We'll talk about that in a second. And then you're left with this. It's the same equation we were working with before. But you know that vertical freakout happens when the denominator is 0, so you set the denominator equal to 0, and you solve. And you say, oh, wait, the vertical asymptote must happen there. Right? So if we were graphing this, I think my graph's in there already. If we were graphing this, we'd say vertical asymptote at -3, so you draw your vertical asymptote, maybe straight. We figured out that the 0 was at 2/3. You'd set the numerator equal to 0, and so I guess at -2.
Later, to the 0, the denominator can the denominator will cancel out with x minus 2. You multiply x minus 2 on this side, and you're left with x minus 4 equals 0. You add, so you're left with this. Add 4 to each side, and you get x is 4. So 1, 2, 3, 4. So it's going to look like that. Well, it'll look like this. Oh, wrong. All right, look like that. So there's our vertical asymptote. Here's our intersect at 4. You can also see that if you put in 0 for your x, if you put in 0 for x and 0 for x, it's asking where it hits this y-axis. Because the x is 0 there, it hits at -2, -4, -2, which is +2, which is right there. So you can get a sense of roughly what's happening to it. Now, and you can play the same game with this. This would look like the the vertical asymptote would be when this denominator is equal to 0, so that happens at -1. So it looks like this. Right? That's the vertical asymptote. I know it hits the x-axis when this is equal to 0. You multiply both sides by the denominator, and so you'd solve for 0 equals 2x plus 3 to try to find when the y value is 0, essentially when it hits that line, right? So you'd get negative 3/2, which is negative 1.5, so negative 1, negative 1.5, someplace like that. All right. And then the y-intercept would be when the x values are 0. So you'd put 0 into the x's, here and here. And so this would be 2 times 0, 0. So you get 3. And so 1, 2, 3, something like that. Cool. And if you graphed it, it would look something like that. Let's get this. So here's the y-intercept at 3 like we predicted. Here's the x-intercept at 1.5. Here's the asymptote at negative 1. Did I write negative 1? Hopefully. There you go. The thing that we haven't seen so far is where does this horizontal asymptote happen? Where does it happen here? Right? Here it happens at 2. Here it happens at 1. Sometimes it happens at 0. It's a little unclear where that's occurring, but we can see what's happening if we think about the cookie idea. Yeah, and so we'll come back and look at these again. But this is the horizontal asymptote. Simplify if you can, and then look at what number the numerator and denominator approach as x gets large, right? And see what overall, not necessarily, sorry, the numerator and denominator, but what value f of x approaches because of the numerator and denominator. So here's an example. I know the vertical asymptote of this is going to occur when the denominator is 0. So when 3 equals 0, so at 5/3. Yeah, so 1 2/3, and so that kind of looks like around here. That's fine. That's easy enough to find. I can't tell necessarily where this is. I mean, it looks like the asymptote's at y equals 2. But unless I have a graph, I don't necessarily want to graph this, or I want to be able to graph this by hand and not on a calculator. I want to be able to figure out where that horizontal asymptote is just by looking at this, and we can. So think about what happens if you put 1 in here and here for x. You'd get 6 plus 2, so you'd get 8, and you'd get 3, but you'd get minus 2, so you get negative 4, right? That's fine. If you put really big numbers in, not just 1, but like 10, or maybe 100 or 1,000, let's put 100 in there, right? Let's put 100, not just 1. This would be 602. Oh, 602. And this would be 300 minus 5, so 295. This is about 600, and this is about 300. This is pretty close to 3, right? If you had a calculator, the tiniest calculator ever, here you go, 602 divided by 295, you get 2.04. If you did this with 1,000 and 1,000 instead, you'd get 6,002, and you'd get 3,000. Sorry, you'd get 2,995. And if you punch it into your tiniest calculator ever, 6,002 divided by 2,995, you get, 2.004. And if you added another 0, you get the message, right? This is approaching a value, right? And it's never going to hit it. That's why it's asymptotic. But it's going to approach this value of 2. And you can see it getting closer and closer and closer to 2. So you don't have to do this with a bunch of numbers. Just do it with a really big number. Think about like 1,000,000. Put in 1,000,000 here. What you can see happening is that if you put in really large numbers into this equation, if you put a really massive number in there and in there, same number, like whatever, 100,000, 10,000. If you have $10,000 and like if this is your bank account up top, you have 6 times that 10,000. This plus 2, if you're talking about 10,000, the 2 is insignificant, right? You're like, oh, I found $60,000. and 2 more. Like, why even say that you found 2 francs, right? This becomes insignificant, and so does the 5. You're like, oh, I have $30,000. Oh, and I lost $5. Nobody cares about the $5. This becomes insignificant, and effectively, this becomes 60,000 over 30,000, which really effectively becomes 6 over 3, which really effectively becomes 2. This is the beginning of limits, and that's the foundation of calculus. And you can see the horizontal asymptote is here at 2. Let's try that with these that we've already been messing with. It looks like, if we graphed this, that this, get rid of those, get rid of that, get rid of that. Gotta make it right. Looks like this has an asymptote at 1, a horizontal asymptote. Play the bank account trick. If you have $1 million there and $1 million there, $1 million. If you have $1 million and you lost $4, it's not worth telling anybody. Nobody cares. And if you have $1 million and you lost $2, it's not. You basically still have $1 million. You're like, oh, I don't have $1 million. I lost $4. You still are a millionaire, right? As this x value becomes really big, as you go this way on the graph, you end up with this 4 being negligible and the 2 being negligible as your x gets really big. And your ratio between the two is 1 million to 1 million, which is 1, right? And that's why this gets closer and closer and closer to 1, but never touches it. And even from the other side, you could do it with negative numbers too, but once you do it with the positive numbers, you just take the money and run. Play the same game here. If you put $1 million in there and $1 million in there, you get $2 million and $3 and $1 million and $1 more dollars. Really, this person, if you put $1 million in here, you multiply by 2. This person has $2 million. The 3 is negligible. This person has $1 million. And then I found one more. No one cares, right? You get 2 million over 1 million, which simplifies to 2 over 1. And you can see this asymptote is up here at 1, 2. Right there. Eh? Provocative. There's an acronym, Bobo Baggins, Bobo. I hate that thing. I'm not going to teach. I don't know what it means. There's 3 cases, and it always works if you think about it. What happens to the overall y value as x gets big? So I'll give you 3 more cases, right? Here's another one, 3 over this thing. Where's the horizontal asymptote? Well, if you put in $1 million in here, you get 3 cookies divided by 1,000,002 people, which is basically 3 cookies divided by 1,000,000 people. If you take 3 cookies and give them to the population of India, basically everybody gets no cookie, right? 3 cookies divided by 1,000,000. All we're doing is saying as you go that way on the x, the denominator gets bigger and bigger and bigger. You're taking 3 finite things and dividing them among all of these people. And essentially everybody gets 0. So the horizontal asymptote is 0. Yeah. Here's another case. Let's move this over here, like that. Here's another case. This one, the numerator had the power of the numerator was smaller than the x power. This is x to the first. You could effectively think of this as x to the 0. So this is the case where the top is smaller than the bottom. That's the Bobo bottoms. Look it up if you want. It's ridiculous. Here's the same idea with this one. Similar. This is where the exponent on the top is smaller than the exponent on the bottom. If you put 1,000 in for x and 1,000 in for x, here you'd get 6,000. Here you'd get 1,000 times 1,000, which is 1,000,000. And even if you have 6,000 cookies, share them around 1,000,000 people, effectively everybody doesn't get much cookie. And you can see this as we add some zeros. If you add, well, let's add some more zeros. You get 6, 2, 3, 4, 6. You get 6 million cookies. But if you divide, we added the 3 zeros, 1, 2, 3. You'd have this times itself. You'd have over 1, 1, 2, 3, 4, 5, 6. Now we need to do that twice. 1, 2, 3, 4, 5, 6. This bottom component is always going to way outpace the numerator because we're squaring it. And so this effectively is going to eventually limit at 0 because you still have, I have what, 6 million cookies over a kabillion people. Basically everybody's going to get no cookies. Even though I have a lot of cookies, I have way more people. And this power in the bottom, since the bottom has a much bigger power than the numerator, it will always sort of approach 0 because you're taking a finite number, a much smaller number, and dividing by a much larger number. Cool. So that's one case. Here's another case, and I'll leave these all out for you. This is the other case if the numerator in the has a higher power, or an equal power, sorry, to the denominator. I know that there's a 1 here, but we're looking at the highest magnitude power. And so these are equal. This is what happens with that. If you put in, again, 1,000,000 into there, well, 1,000 into there, and 1,000 into there, into the x's, essentially if you went over to 1,000 on the x, this would give you 1,000 times 1,000, so and times 8, so 8 million. And this would give you 2 million minus $1,000. If you have a $2 million, giving away 1,000 is not even worth your time to talk about. So essentially, this piece becomes negligible because the power is smaller than this, and the squared, this piece will outpace this 1,000. So this piece becomes negligible. The 1,000 becomes negligible, and the ratio between 8 million and 2 million is the ratio of 8 to 2 is 4, right? So essentially, the asymptote happens if these are the same power when these are equal, right? So you see that happen at 1, 2, 3, 4. Neat. Okay, and then finally, someone let me out of my cage. Yeah, time for me is nothing because I'm counting no age. All right. Our last case, if I get my head out of the way, is with the numerator and denominator, the numerator power being bigger than the denominator power. We don't see this often in the IB, but I just want you to see the same thing happens. If you put 1,000 in there and 1,000 in there, you get 1,000,003 in the numerator. Something like that. And 1,001, 2, 3, 1, 2, yeah, in the denominator. Essentially, this outpaces this exponent, makes this so much bigger than this denominator. It'll never converge. So you don't see this horizontal asymptote. What you get is a slant asymptote, and we're not interested. That's beyond the scope of our course. So you might see this, and you can just say that it has no asymptote, but that's why, because this gets so much bigger than this denominator that it never converges nicely like these others do. So here's the synopsis of all of that. Yeah. And we're going to try that out with a couple of examples. So here's 2 examples. All we want to do is find the zeros, find the horizontal and vertical asymptotes. Essentially, we're going to try to draw these. Yeah. Did we? I think we already messed with these a little bit. But essentially, the zeros for this were when if you make x 0, that means you're right on this y-axis because you're not over one way or the other. So x is 0. You put zeros in here and here, and you'd get -4 over -2, so that's 2. So the y value is 2. You could do the same thing with looking at where this occurs, where it hits this line. The y value is 0 there, so you set this equal to 0. You multiply both sides by that. You solve. You get x is 4. So 1, 2, 3, 4, like that. And then the vertical asymptote occurs when the denominator is 0. So when x minus 2 equals 0. So that occurs when x is 2. So here, and then the horizontal asymptote occurs when we put in big numbers into the x and see what happens. So if we put in 1,000,000 and 1,000,000, you get 1,000,000 minus 4 and 1,000,000 minus 2. Essentially, this is 1,000,000 divided by 1,000,000, and it approaches 1. So the horizontal asymptote is at 1, so it looks like that. Cool. And then we approximate. So it goes up, goes through here, looks like that. And this one should do this, look at that. Yeah. And that's where we got this from. Ta-da! Cool. It doesn't need to be anything bigger than that. I need asymptotes and I need zeros. Neat. Let's try this one. Same thing. Asymptote. Well, let's do the zeros. So the zeros occur when the x is 0 on the y-axis. So put zeros in for these two. They cancel out, you get 3 over 1. So this occurs at 3, 1, 2, 3, y-intercept. The x-intercept occurs when the y is 0. So we put in a 0, multiply both sides by that, goes away. And you solve, you get -3 and -3 halves. So -1.5, so there. That looks fine. Vertical asymptote occurs when the denominator is 0, so when x plus 1 is 0, so that happens at x is -1. So right here. Make sure I got my signs wrong before I lead us astray. No, that works. That works. And then the horizontal asymptote occurs when we go really far to the right or really far to the left. So put in 1,000,000 into there, you get 2,000,003 divided by 1,000,001. That's essentially 2,000,000 divided by 1,000,000, and that ratio is 2 to 1. So it should converge at horizontal asymptote at 2. So if you connect your dots, it should look like that, and then this like that. And that's all the closer you need to get with that. You need that point and that point, roughly what side they're on. Right? If you're not sure, you can test a point too. You can see like 10. What do you get out if you put in 10? Plot another point. It'll help you visualize the graph. Neat. Okay. One little piece is that sometimes there are holes in the graph. Like if you simplify first, often you can make this easier to work with. If you simplify this, you could factor the top, cancel a few things out. The x minus 3's cancel, and you're left with x plus 3. So if you graph this purple, it doesn't look like a hyperbola. It looks like a straight line, which is kind of strange, but it's because it simplifies to this. The interesting part is x plus 3 looks just like this, except it's continuous. This function is not continuous because there's a problem with this denominator. The denominator can't be 3. And so if you graph this in your calculator, it won't show you a hole, but if you ask for a value at 3, it'll say error because there is no value at 3. You can't put in 3 there. It's called a hole. Cool, it's an omitted point on a graph. All right, so let's put it all together and see if we can make this work. I want you to try to find zeros, vertical and horizontal asymptotes, and graph this. Give me a pause until you've done that. Put my big head back in here. All right. So the x-intercept happens when y is 0, so let's make this 0. We would multiply both sides by the denominator, and it would cancel out, so you'd really have 0 equals 4x plus 8. Subtract, divide, you'd get x is -2. So x is -2, that's our x-intercept. We know where this occurs, the x is 0, wherever it hits there, the x is 0, so we can, into our function, put zeros in for the x's. These multiply to 0, and you get an asymptote, or sorry, a 0 at, also at -2, at -2. So -1, 2, there. Cool. We get a horizontal asymptote. Sorry, let's do the vertical. We get a vertical asymptote when the denominator is equal to 0, because we can't divide by 0. So when is 2x minus 4 equal to 0? Add 4, divide by 2, x is 2. Ooh, a lot of 2's in here. So vertical asymptote at x equals 2. So we get this thing going on. And what color I'm going to use for green? You get a horizontal asymptote when as you go really far one way on the x or really far the other way on the x. So essentially putting really big numbers in. So let's put 1,000,000 into both the x and that x. You get 4,000,008 and 2,000,000 minus 4. Essentially these become negligible and you get a ratio of 4,000,000 to 2,000,000, which is a ratio of 2. A lot of 2's. So you get a horizontal asymptote at 2. Looks like that. And so when we graph this, black I guess, connect your dots so it'll look something like that. And up here, just give it roughly a mirror, right? The big things they're looking for is zeros, asymptotes. Cool? It's a sketch. If you want a drawing, use your phone or calculator. Not your phone, your calculator. That's it. Try the asymptotes problem from the packet set, and best of luck to you.